Okay, in this tutorial we're looking at section 8.6, which is integrals involving inverse trigonometric functions. Okay, so the first part is on integrals involving the inverse sine function. Okay, so we get from our derivatives of our inverse sine functions, then we can also look at some integrals. So an integral of 1 over the square root of a squared minus x squared dx is equal to the inverse sine of x on a plus c. And that's for a is larger than 0 and the modulus of x is less than a. So we'll have a look at a couple of worked examples. So at worked example 27, okay, where we need to integrate 12 over the square root of 36 minus x squared dx. Okay, so for this one we can bring our 12 out the front, so that we've got 12 times the integral of 1 over the square root of 36 minus x squared dx. Okay, what we can do is think of that as 12 times the integral of 1 over square root of 6 squared minus x squared dx, and then that's going to equal 12 times inverse sine of x on 6 plus c. Okay, so that one was pretty straightforward. Okay, if we have a look at the next one here, okay, where we've got the integral of 4 on the square root of 49 minus 36x dx. What we need to do is a substitution. So we're going to say let u equal 6x. Okay, well our u squared equals 36x squared, okay, which we like. Okay, our du dx is going to equal 6, which means dx on du is 1 on 6, so dx equals 1 on 6 times du. Okay, which means what we can say then is that we've got the integral, okay, of 4 over square root of 49 minus u squared times 1 on 6 du. Okay, what we're going to do is bring our 4 on 6, or 2/3, out. And so we've got 2 on 3 outside of 1 over square root of 7 squared minus u squared du. Okay, which means we're going to get 2 on 3 times the inverse sine of u on 7 plus c. Okay, sub our u back in and we get 2 on 3 times the inverse sine of u was 6x, so it's going to be 6x on 7 plus c. So we can definitely use our skills of our substitutions that we've learnt in previous tutorials on these type of questions. Okay, so we go on and we look at integrals involving the inverse cosine function. Okay, so this time it's the integral of -1 over the square root of a squared minus x squared equals inverse cos of x on a plus c. Okay, and that's where this time a is larger than 0. Okay, and the modulus of x is also less than a. So we're having a look at worked example 28. Okay, now I've simplified the question here a little bit, saying that we need to find the integral of -4 on the square root of 81 minus 25x squared dx if the function goes through the origin. Okay, so what we need to do, okay, is recognise that the gradient of a curve is given by dy dx. Okay, so what we need to do here is do a substitution. Okay, and we're going to say let u equal 5x. Okay, because then we've got, well, u squared equals our 25x squared, which is what we need. Okay, if we look at our du dx, well, that equals 5. So our dx is going to equal 1 on 5 du when we do our rearranging. Okay, so we can set up our integral now and say that we're integrating from -4 square root of 81 minus u squared times 1 on 5 du. And what we're going to do is we're going to take our -4 on 5, sorry, just our 4 on 5 out. Side of -1 over the square root of 9 squared minus u squared du. Okay, well that means that we're going to get 4 on 5 times the inverse cos of u on 9 plus c, plus c, 4 on 5 inverse cos of u on 9 plus c. Try that again. Okay, we sub our u back in, which was 5x, so we say that we've got 4 on 5 times the inverse cos of 5x on 9 plus c. Then we know we go through the origin, okay, because we say, well, this is equal to y, so our origin, we say 0 equals 4 on 5 cos of, well, 5 times 0 is 0, so we end up with cos of 0 plus c. Okay, which means we get 0 equals 4 on 5 times pi plus c, so pi on 2 plus c. Okay, cos is equal to 0 at pi on 2. Okay, so when we rearrange that, okay, it'll just come up here, we get our c equals negative 2 pi on 5, because we have 4 and our 2 can cancel down. Okay, that means that our equation then is y equals 4 on 5 inverse cos of 5x on 9 minus 2 pi on 5. Okay, and we're done. Okay, so have a look at integrals involving inverse tan function. Okay, so again, because of our derivatives of our inverse tan, we find that the integral of 1 over a squared plus x squared dx is equal to 1 on a inverse tan of x on a plus c. Okay, and this is for x is an element of all real numbers. Okay, so we're looking at worked example 29, and we need to integrate 12 on 36 plus x squared. Okay, we can simply take our 12 out side and have 1 on 36 plus x squared dx, okay, which is going to be 12 outside of 1 over 6 squared plus x squared dx, which means we get 12 times 1 on 6 inverse tan of x on 6 plus c. Okay, 12 times the 6, well, that's going to give us 2. I'm going to say we've got 2 times inverse tan of x on 6 plus c. To finish off. Okay, when we have a look at this question here, we've got to find the integral of 4 over 49 plus 36x dx. Okay, what we can do there is do our let u equal 6x. Okay, that means that u squared equals 36x squared. Okay, it also means that our du dx is equal to 6, which means our dx is equal to 1 on 6 times du. When we rearrange that, which means we can set up our integral now, okay, and say that we've got the integral of 4 on 49 plus u squared times 1 on 6 du. Okay, we can bring our 4 on 6, which is 2/3, out the front. Okay, so we've got 1 over, and so 7 squared plus u squared du. Okay, which means we get 2 on 3 times 1 on 7 inverse tan of u on 7, okay, plus c, okay, which means we get 2 on 21, okay, inverse tan, so it should be an inverse tan, sub u back in, which is 6x on 7 plus c. Okay, is our answer there. So we'll keep moving on. Okay, so we've got, and of course we can do these ones, all the examples that we just have, could have for definite integrals where we've got our terminals. Okay, so we can have examples where we've got integrals involving completing the square. So if we complete the square on 1 on ax squared plus bx plus c, where a is bigger than 0 and the discriminant is less than 0, okay, then we do that to use the inverse tan function, or we can complete the square on 1 over the square root of ax squared plus bx plus c, where a is less than 0 and the discriminant is greater than 0, to use the inverse sine or cosine rules. So having a look at worked example 31b, okay, you can have a look at 31a if you like as well. Okay, so when we have a look at our quadratic here, okay, we need to express the quadratic factor in the denominator in the completing the square form by making it into the difference of two squares. So what we do there is we say then that our 21 minus, so 12x, sorry, our 21 minus 12x minus 9x squared, okay, well we can say that that's equal to 21 minus 9x squared plus 12x. Okay, well we can say that's 21 minus, we can say 9x squared, okay, plus 12x plus 4, okay, plus 4 means that we end up getting 25 minus 3x plus 2 squared. Okay, so what that means is we can say then that our integral is really the integral of 1 over 25 minus 3x plus 2 squared. Okay, well if we do that, and that's dx. Okay, we should recognise this is a tan one, so we'll come over here now. We'll say, well, let u equal 3x plus 2. Well, u squared equals our 3x plus 2 squared. Our du dx is going to equal our 3, okay, which means dx equals 1 on 3 du, okay, which means then our integral becomes 1 over, oh sorry, it's not going to be our tan, sorry, I forgot our square root sign. So it won't end up being our tan, sorry about that, okay, which means we end up with 1 over the square root of our 25 minus u squared times 1 on 3 du. Well, we can bring our 1 on 3 at the front. So we've got 1 on 3, it's the integral of 1 over the square root of 5 squared minus u squared du. Okay, well we're in our sine form, so that means we're going to be 1 on 3 inverse sine of u on 5 plus c. And we can sub in our u value of 3x plus 2 on 5 plus our c. Okay, so it's just that process of doing a linear substitution after doing our completing the square. Okay, so we'll keep moving on to our last worked example, which is worked example 32. Okay, and this is talking about integrals involving substitution and inverse trigonometric functions. So we can break up complicated integrals into two manageable integrals using the property of splitting up our integrals in two separate parts. Okay, so we want to find the integral of 4x plus 5 over the square root of 25 minus 16x squared. So what we're going to do there, okay, is actually think about splitting this fraction up and saying that we've got 4x over the square root of 25 minus 16x squared, okay, plus 5 over the square root of 25 minus 16x squared dx. Okay, now you can write them as, what we do is we can write it as separate integrals. So we're going to say that we've got the integral of 4x over the square root of 25 minus 16x squared dx. Now we're just going to worry about this part at the moment. Okay, we're going to leave it the rest for a little while. So what we're going to do is we're going to rewrite this as 4x times 25 minus 16x squared to the negative half dx. Okay, now we need to do that because of our x on the top line. None of our inverse trig has x on the top line. So what we then need to do is let u equal our 25 minus 16x squared. Okay, which means our du dx equals negative 32x. Okay, which means our dx on du is equal to 1 over, or negative 1 over 32x, which means that our dx is equal to negative 1 over 32x du. Okay, so that means that we can rewrite this part of the integral, okay, as, well, we've got our 4x, okay, times our u to the negative half, okay, times by negative 1 over 32x du. Okay, well our 4x and our 32x can cancel out. Okay, leaving us with 1 on 8, or negative 1 on 8, which we can bring out the front. And so we've got negative 1 on 8 as the integral of u to the negative 1/2 du, okay, which works out nicely. So we end up taking that. Okay, we end up, when we simplify as well, with negative 1/4 times the square root of u, okay, which when we sub our u back in equals negative 1/4 times the square root of our u was our 25 minus our 16x squared. Okay, and you say plus c if you like, which we'll need to at the end, but we can just do one constant at the end, it doesn't matter too much. Okay, so then we need to look at our second half, okay, which is our integral of our 5 over our square root of 25 minus 16x squared, okay, dx. Okay, well we can, we've already used u, so you really shouldn't be using u again because you've already defined u as this. So if you're going to define u as something else, it doesn't really make sense. So instead what we're going to do is say let v equal 4x, okay, v squared equals 16x squared, okay, and dv dx is going to equal 4, okay, so that means that dx is going to equal 1 on 4 dv. Okay, so we can set up our equation now. So we can say that our integral is now of 5 over the square root of 25 minus u squared, okay, times by 1 on 4 dv. Okay, so that should be a v, I've done it myself. It's 25 minus v squared. Okay, we bring our 5 on 4 out the front. Okay, so we've got 1 over square root of 5 squared minus v squared dv. Okay, which equals our 5 on 4. Well, this is in our sine form. So inverse sine of v on 5 plus c. Sub it our v back in, which is 4x, so we get 4x on 5 plus c. So if we bring it all together, okay, then we can say our integral of our 4x plus 5 over the square root of 25 minus 16x squared dx, okay, is going to be equal to, well, we'll put this one first because this is a negative, 5 on 4 inverse sine of 4x on 5 minus 1/4 times the square root of 25 minus 16x squared plus c. So even though we had a c here and a c here, well, constant plus a constant, yes, you can think of that as 2c, but a constant plus a constant is still just a constant, so we can just write c at the end. Okay, so that's everything there is for this section. I don't think there's anything terribly difficult in this. If you've been able to get through some of the linear substitutions and things like that in previous sections, I think you'll more or less find these questions not too challenging.